In the last section for this bit on volumes of revolution, we're going to look at what happens if the axis of rotation leaves a gap between the figure that we are rotating. So here is an example. I have this rectangle here. What we looked at in the previous video was if I were to rotate it about this line, I would get a disc. However, if I rotate it about this line instead, you can see that there's this gap between where I'm rotating and where the figure actually begins. And so let's look at what that looks like with just a basic rectangle, because that's what we can see kind of the easiest. We know that when you rotate a rectangle, you get a cylinder. However, what is that going to look like with this gap in the middle? Well, it's going to come towards us just the same. You can see that we're kind of tracing two circles when we do that. And so what you see if we turn this sideways is our figure has a hole in the middle. This is where the solid is. So this is all solid, but this is almost like a roll of toilet paper. You've got this hole in the middle of the graph right here. That is space that we don't want to count towards our volume. The volume is only going to be this right here. So instead of calling this a disc, this is called a washer. If you've ever seen, when you put stuff together with a bolt, you have like a bolt and the nut and the washer that all goes together. Or if you've ever played like the game Washers where you throw them into the little bucket, that is what we call it when we have this negative space on the inside. Now that's a pretty straightforward example when we just have a disc. What we saw with the discs was that we wanted like infinitely many slices that looked like this. And so we basically want super, super skinny washers is what we're going to try to find here. Here's an example. This is basically the one that we ended the notes with in the last section, similar to it. What we looked at in the last section, once again, was we rotated this around this horizontal line. And if we do that here, you end up with kind of like a solid football-shaped thing. However, if instead I rotate this about the x-axis, once again, it's going to trace this path and leave that negative space on the inside, which we have to account for. So let me turn this sideways so we can kind of see what is happening here. When we rotate this, you can see how it's tracing out this circular shape, but we have, it almost is like a bead, those wooden beads that you make necklaces with when you're a little kid. We have this thing that has a tube missing from the inside of it, essentially. And so when we slice this into a bunch of slices, each of those slices is going to have a hole in the middle of it, and that we need to take account for. And so that is why the final thing that we're going to look at here is the washer method, which is the same as the disc method. It's just going to account for that negative space. So we have to take two different radii into account. If we have our region, which is this yellow rectangle here that would rotate to make that washer shape thing, the disc with the hole in the middle, we have the total distance between the top of the rectangle and the axis of revolution. That would be like finding the volume if this was a solid disc, if there was no hole in the middle. Then we need to subtract out the negative space, which is going to be this little radius, the inner radius we call it, which is the radius of just the negative space. So we're going to find the volume of the whole thing without the hole in the middle minus the volume of the hole. And that's going to leave us with just the washer on the outside. Now, once again, by using our properties of integrals, if I do the integral of big R squared dx or dy, whatever, minus the integral of little r squared dx or dy, using our properties of integrals, we can combine that into a single integral to make this a little bit easier. The main thing to keep in mind of when do you need the disc method versus when you need this washer method, You are looking for a gap between the axis of revolution and the region that is being rotated. If my axis of revolution had been here, we would not need 2 radii because there is no hole in the middle. There's no space between the axis of revolution and the figure itself. So that would just be a straightforward disc. But when there is a gap, that is when we have to use this washer method. And as always, you need a picture, okay? You always want to be able to sketch this out. So here is the same graph that we ended with in example 5, but we're going to rotate around a different axis of revolution. So we want to rotate this graph about the x-axis this time. When we did this before, we rotated it around the line y equals 2, which meant there was no gap in the middle. But if I am revolving around the x-axis, so we're rotating here, we have this negative space, okay? So if we use the representative rectangle that they gave us, which we could really, again, choose to draw anywhere, we have capital R is going to be the total distance here, and then little r is going to be our inner radius, that's the negative space, all right? So capital R is going to be our function. That's all the way from the graph down to the x-axis. So that's 4 minus x squared over 4. Little r is just going to be 2 because this horizontal line y equals 2 is always going to be the top. So that little distance r there is always going to be 2. When we set this up, because we square the 2 radii separately, this is going to come out differently than the first one we did. Now, we're rotating about the x-axis, which means our integral is going to be dx. It's still going to be pi because of the cylinder aspect of it when we rotate. So we want the integral from, choose your limits from the x-axis, so -3, to +3. And then we want outer radius squared. So that's going to be 4 minus x squared over 4 squared minus inner radius squared dx. Once again, if I was trying to grade this myself, I would want you to just leave it like that because I can very clearly see all of your pieces here. This is big R, this is little r. If you start squaring things and foiling things, then I have to kind of go backwards. Now, to actually evaluate this and get the answer, you will have to multiply that out and actually do the algebra. But if it's just a question where it's asking you for setup, then I would just go ahead and leave it set up just like that, okay? So that's the only extra thing that we have to take into account when we're looking at the washer method is subtracting off the volume of that inner void area. Okay, so here is another one, and this is very similar to how a lot of these problems are going to look on your homework. You're going to use one region and rotate it a whole bunch of different ways. So we want to find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the indicated lines. So first we want to rotate about the x-axis. Second, we want to rotate around the line y equals 3. Now they did not give us a graph here. So the first thing that we need to do is graph it. That second one is a line, so that is pretty easy. We want y equals x plus 6 is going to look like this. Okay, y-intercept 6, slope of 1, so that's our graph there. Now the other one, 6 minus 2x minus x squared, you could very easily set up a xy table. What I'm going to do is use the table function in my calculator to get some points. So in my y1, I'm going to type my 6 minus 2x minus x squared. And then I'm going to go to my table. And let's see, I'm going to do -2, -1, 0, 1. Whoops. What did I do? 0, 1, and 2. And so I get the ordered pair -2, 6, -1, 7, 0, 6, 1, 3. and 2, -2. So it looks like the vertex here, if I plug in -3, let's see what we get, +3. So yes, it's going to be a parabola that looks like this. And so we can see here is the region that we are going to be revolving. Okay, so first question, when we revolve about the x-axis, like I said, there's problems like this on your homework where it gives you a graph and then asks you to do a bunch of things. Sketch yourself a new picture every single time because you want to be able to mark all over it. So let's sketch out just a rough sketch of what this looks like over here. We have this figure that looks kind of like this. That's sort of our shape, okay? And we are going to revolve about the x-axis, which is right here. So that's where we are rotating. We need to consider the rectangle that is going to make our washer. And from that information, I know that big R is going to go all the way to the axis, which is the x-axis, and little r is going to be the void space underneath. I always sketch that picture, always, because this is so visual and it's kind of hard to figure out without sketching this picture. I feel like my BC students like fought about sketching this out and realized very quickly like they need to still draw the picture. It doesn't make a lot of sense without seeing the picture there in front of you. So to find that rectangle, we have the top curve, which is the parabola. So that's your big R is the top curve. Big R is going to be 6 minus 2x minus x squared. And little r is below the bottom curve, which is the line. So little r is going to be x plus 6. And we can see that from our picture, okay? So, again, we're rotating around the x-axis, which is horizontal. So that means we're going to rotate dx. And so now you should be able to set up your integral. So I'm going to ask you to pause and try to set it up yourself and see what you think. 3 seconds. This is what you should get. Since it's dx, we want to go along the x-axis from -3 to 0. Those are our boundary points. You can confirm that by solving the system. And so we have big R squared minus little r squared with respect to x. Don't forget the pi in the front. And that is what that should look like. Now, if we want to actually find the volume, then we need to integrate that either by hand or for this one, I would probably use a calculator. You could do it by hand, but that'd be a lot of multiplying out and stuff that gets kind of ugly. So I would just use a calculator there. For B, we want to use the same figure, but we want to rotate around the line y equals 3. That is also a horizontal line, but that is the line that goes through right here. That is going to change what our radii are because the radius is always going to measure to the line you're revolving around. So again, like I said, I sketch myself a new picture every single time. So here's what we've got. Again, it's kind of a weird crescent-y looking figure like this. And our axis of rotation is this right here, y equals 3. That is the line where we are rotating. All right, so that makes our radius a little bit different. Our big R is going to measure from here to here. So the top curve down to the line y equals 3 because that's the center. That's where we're going to rotate around. That's going to be big R. Little r is going to be this distance right here. Okay, that's the only place that there's going to be a gap. This negative space in here is not part of our concern for this particular problem because we're not rotating around the x, we're rotating around this dotted line y equals 3. So we need to figure out what our radius is going to be. So capital R is going to be from the top curve, which is the parabola, but it's going to be minus the 3 minus the gap here. This is always going to be 3. Okay. So we need to do top curve minus bottom curve. In this case, the bottom curve is the line y equals 3 where our radius stops. So this is going to be 6 minus 2x minus x squared minus 3, because we don't want those bottom 3 that take us all the way down to the x-axis. Remember that the function always measures from the x-axis up to whatever point you are trying to get to. So if I wanted to measure just from here up to a point, I have to subtract off this void space here, which is why we have to subtract 3 there. So that makes our big radius 3 minus 2x minus x squared, if you want to simplify. And then little r, in a very similar fashion, is the line x plus 6, again, minus the 3 for that horizontal line where we are stopping, okay? And so we get x plus 3. So the volume here would be pi times the same integral, because we're going along the x-axis still. It's a horizontal line, so we want to go horizontally from -3 to 0. Little r big R this time is going to be 3 minus 2x minus x squared minus the inner radius, which this time is just going to be x plus 3 squared dx. That is the trickiest part, is figuring out how to adjust, okay? If you think of, again, I'm going to go back to this original graph up in the corner. The function itself, y, is measuring this entire distance right here, okay? If the whole thing is y, and this little bit right here is 3, we want y minus 3 to give us this remaining piece. Well, y was 6 minus 2x minus x squared, and so that's why we ended up putting that together the way that we did. This takes a lot of practice, you guys, so don't get too discouraged, and always draw your pictures.